morning and welcome to this next lecture on sound and structural vibration. We stopped over here last time. We were looking at influences of uncoupled modes on each other in finding the new coupled resonances, and this was the last statement we made. A lower uncoupled resonance, whether it be panel or acoustic, will push a higher uncoupled resonance, whether panel or acoustic, to a further higher value. Okay. Similarly, a higher uncoupled resonance will push down a lower uncoupled resonance to a further, or let us say push a lower uncoupled resonance to a further lower value. Okay. Now there are further details in the paper which are, I guess, secondary in nature. For example, if we consider three panel modes and 3 acoustic modes, okay, then we will have the matrix look like this, or the table look like this: B1, B2, B3, and then the coupling values are 0.3648, 0, 0.1216, and you have 0, 0.3439, 0, and then minus 0.1719, 0, 0.3095. This is the A1 mode at 0 resonance. This is the A2 mode 100 at 113 hertz or so. Then they have A3 mode 200 at 226 hertz about, and this is at 140.51, this is 156.72, this is 183.74. So we have 3 acoustic modes, 3 panel modes. So all the vectors Vi's and Ui's will have 3 cos 1 dimension, and there will be I going from 1 to 3. That means I will now have 3 terms. I will now have 3 terms in a product, okay, which will have to be set to 0. Okay. And very interestingly, this structure of the matrix tells you many things, that B2 and A2 are coupled together, okay, but in no other place do they couple, so they form a separate system. Okay. So the matrix approximately looks like what? The determinant U1 transpose V1 into 1 plus U2 transpose V2, 1 plus U3 transpose V3. So you will find that the second one forms its own system. Okay, so they will not couple with anything else. They form a separate system. So their system can be studied separately. Their coupled resonances. So A2 will influence B2 and B2 will influence A2 only. There is no other. B2 will not influence B3 or B1 or A1 or A3. No. So the contents of the matrix tell you how the coupling goes. Okay. So now you can study their. So you can see that A2 is 113 and B2 is 156. So A2 will push B2 new to a new higher value, whereas B2 will push A2 new to a lower value. So they will do that to each other. Now you have to deal with 1 plus U1 transpose V1 and 1 plus U3 transpose V3 equal to 0, and any one can be set to 0. Okay, any one of the values can be set to 0. So now you will see that this is related to first acoustic mode, the A1 mode. This is related to A3 acoustic mode. Okay, now suppose you are trying to find B3 nu, okay, or omega p nu of 3. Okay, now that can be found either using the first term, because that can be set to 0, or this term which can be set to 0. So there are two ways you can find this omega p nu 3. So how to do that? So we set up a criterion. We set up a criterion which is of this form. We set up a criterion. Which term to use? The criterion is this. It's given the C, which is absolute value of C n m square divided by that acoustic mode squared minus that panel mode squared, whichever is higher. Okay, what does that mean? I now want to find the new coupled value of B3, but B3 couples to the first acoustic mode and couples to the third acoustic mode. That means I can find it using the term related to first acoustic mode or the term related to third acoustic mode. Okay, so now how to do that? So the criterion is 0.1216 squared divided by the resonance squared of acoustic mode minus resonance squared of panel mode. So 0 squared minus 183.74 squared is our hertz, so into 4 pi squared, the absolute value. Okay, then similarly 0.3095 squared divided by 4 pi squared into 226.67 squared minus 183.74 squared. Okay, so in this it turns out that this value is higher. This value is higher. So we will use this term. Okay, so we will use the 1 plus U1 I mean U3 V3 term and try find out my omega p nu 3. Okay. So now let me move to the paper and show you the paper if there are any details that I want to add. So here is a table. Okay. So here is a table which has the what shall I say, the number of modes that are included here in the calculations. Okay. So in the first calculation, A1 acoustic first mode, B1, B2, B3 are included. In the second calculation, 2 modes are included and 3 panel modes, B1, B2, B3 and so on. The third calculation, 3 acoustic modes, A1, A2, A3 and B1, B2, B3. Okay. And you can see now the, of course the rigid body mode remains. The second acoustic mode, okay, originally at 113, okay, in the first calculation is pushed down to 102.55, second calculation does not change much, third calculation to 0.07, okay, and so forth, and it starts to settle down. Okay. The higher and higher modes do not have an influence on A2. Similarly, the B1 mode, it starts off with 140.51, in the first set goes to 151.9 and more or less remains there and maybe slightly drops. Okay. The next, the B2 mode at 156.72, okay, is dropped to 156, is raised to 173, is remains as 173, dropped a little to 172.4 and so on, and starts to settle. Okay. So any mode is influenced by values of resonances close by. Okay. If you start including modes that are further and further away in resonance, there are these A1, A2, A3 terms which have frequencies in the denominator. Okay. You have omega n square minus omega square type terms in the denominator. So as omega n starts to become larger and larger for a higher mode, their influence starts to become less. Okay. So if you are at B2 or B3 around 150, you start taking in resonances which are of 300 or more, their influence will die down. So a coupled value settles down quickly. Okay. So this table shows that. So you have B3 at 185 drops to 174 and drops maybe slightly and settles down. Okay. So that is the story of how coupled resonances are formed, okay, in a panel cavity interaction system for light loading. Okay. The story is told for light loading. Okay. So let me get back to my iPad and continue my lecture from there. Okay. Let me do this. This should be 3. Now I want to make a few general comments before I proceed. So let me take a blank page. One is that I forgot to mention earlier, suppose we have, let us say, this situation B1 and B3, of course B2, and this happens to be 0 and this happens to be some number, and this is 0.3648 and this is A1 which is 0. First of all, through this B1 and A0 couple, that is for sure. Similarly, B3 and A0 also couple, okay, and because of the 0, B2 and A1 don't couple. But earlier B1 and B3 were orthogonal. Okay. But now because both of them share a non-zero number with A1, those two will also couple, those two will influence each other. Okay. So what essentially that means is that when you get a coupled B1 mode, there will be a component of B3 in it, or when you get a coupled B3 mode, a modified B3 mode, there will be a component of B1 in it. Okay, that's one thing I wanted to mention. The other thing I wanted to mention here is this. In case you are wondering how I am putting in omega P1 nu or P3 nu, so we have this expression which is the determinant, omega P1 square minus omega square plus something in the numerator, omega P2 square minus omega square plus omega P3 square minus omega square is equal to 0. So if I multiply all the denominators, find the LCM, this is a polynomial. The polynomial with omega to the power 6, or rather we see it as omega square whole cube. So I get 3 roots. Okay, and each of the form plus minus something. So I get 3 roots. What are the 3 roots? I get omega P1 nu, I get omega P2 nu and omega P3 nu. Okay, and each of these will solve this expression. Each of these solves this expression. That's why I deliberately put P1 nu and observe the relations, whether it should be bigger than omega P1 or less than omega P1 and so forth for small fluid loading. So that's how I am putting omega P1 nu ahead of time, if you have not followed what I am saying. Okay, so let us get back to where we are. So now we will move or study another system. Or a next problem. Okay, let's study the next problem. So far, let me just recapitulate. First problem was the classical Creighton's problem. Creighton's problem, okay, where you looked at fully coupled dynamics. Then second was the structural acoustic waveguide. Again we looked at the fully coupled dynamics. Okay. Then third problem was this panel backed by a cavity. Okay. Here also we looked at the fully coupled dynamics. Now we are going to look at a very traditional problem of a radiation or sound radiation from a plate or a panel. I use it interchangeably, from a panel set in a rigid baffle, It's again a very traditional problem in sound structure interaction. So this is a rectangular panel, okay, a rectangular panel. So now what do we have? We have a plate or a panel. To begin with, let us say it is simply supported and it is set in a wall. It is set in a wall that extends to infinity in all directions. Okay. That wall is called a baffle. Wall is called a baffle. And this plate flexes. This wall is rigid, that means velocity is 0 on the wall, and the plate vibrates flush mounted with the wall with simply supported conditions. Okay. Now the implication or need for this wall is that if there is no wall and the plate starts to vibrate and pushes the air, then the air finds an easy path to go behind the panel. So if the plate pushes, let us say plate is here and starts to push the air and there is no wall behind, this is the wall, then the pushed air will not move forward but it will escape to the back side. Okay. And so it will make the radiation inefficient. Okay. So if all the pushed air ends up on the back side, then there will be no sound heard here, and therefore you need this wall. Okay. And that is also the reason why our speakers, okay, our acoustic speakers or music speakers have this backed box. There is a box behind your cone. Okay. It's for the same reason, to prevent communication of air to the back side. Okay. So that speaker is efficient. So we will study this system. Now as I said, some background or a full course in acoustics is required, so I will take the cue from there. So in acoustics we have this equation, which is P of R dash is equal to the integral of G del P dot N minus P del G dot N ds. Okay. It's called the Kirchhoff-Helmholtz integral equation, where G is a Green function. Okay. So whether an exterior problem or an interior problem, let us say we have this situation and we are looking for some value at R dash, a location at R dash, we are looking at pressure, we want to know the pressure. Okay. And on this surface we know conditions, we know pressure conditions, okay, and we know del P dot N, which is velocity conditions. Then we can use this integral, to find the pressure at a point R dash using this integral. So we integrate on this surface. Okay, that's what KH integral says. Okay, so on a surface, so suppose there was sources here, some kind of sources here, whatever number of sources, whatever the nature of sources. Okay, you would have computed using each source and add it up over here, etc. Doesn't matter. If you enclose the sources in a hypothetical surface, the hypothetical surface, not a real surface, and on the surface you manage to find the acoustic particle velocities and pressures, if you manage to find, then you can find the pressure at any location now using this integral. That's what KH integral says. And G is a Green's function. Okay, it can be a free space Green function, it can be some other suitable Green function, okay, for a suitable situation. Now when this is specialized, when KH integral equation is specialized to flat geometries, that means now the radiator is a flat, it's a flat radiator, okay, planar radiator, flat geometries, planar geometries, okay. You can find another Green function, you can find a new Green function, okay, such that new Green function, let us say G, such that del G dot n equal to 0 on the flat surface, flat radiator surface, okay, and the G value becomes equal to twice the free space Green function, okay, free space Green function, okay. So now if I rewrite my KH integral for this flat geometry, it becomes equal to integral twice G del P dot n ds, okay, where G now is the free space Green function, okay, and what is del P dot n equal to? That is equal to minus rho del V del T dot n, okay. So if I include it in here, I get P of R dash is equal to integral twice e to the power of minus jk. Now I am putting the form of the free space Green function, okay, let us say R bar dash divided by 4 pi R bar dash minus R0, okay, into minus j omega rho V dot n ds, okay. For a harmonic case, del B del T is j omega V, that is what I have done for a harmonic case, okay. In addition, in the KH integral, n points away from the direction of interest, away from the region of interest, okay. Now we switch to the region of interest, and so we make it a plus, okay, we make it a plus. So let me rewrite my equation. My pressure at some location r dash, okay, let me make it a vector here, is equal to integral over the, let's say, the entire baffle now, entire plane, okay, to begin with, twice e to the power of minus j k magnitude r bar dash minus r0, okay. This is the field point or the receiver point, okay. This is the transmitting point or source point, source is better, divided by 4 pi magnitude of r bar dash minus r0 bar, okay, into j omega rho velocity dot n ds, okay. Next, of course, I will say that the baffle is rigid. The baffle is rigid. That means the V there is 0. Only plate vibrates. Only plate vibrates. And therefore, this integral happens over the surface of the plate. Okay, so this integral is over the surface of the plate. Okay, so this pressure at an interrogation point is integral over the panel surface of e to the power of minus j k r dash minus r0 divided by twice pi r dash minus r0 j omega rho ds. Okay. Now this is called the Rayleigh integral. This derived version just for planar surfaces is called Rayleigh integral. Okay. Now we will go and start deriving the expression for a pressure. We are running out of time here, so we'll do that in the next class. Thanks.